Welcome to JavaScript Security Best Practices course here on Pluralsight. My name is 𝕨𝕐𝕟𝕚𝕟𝕜 and in this course I will teach you how to write more secure and robust JavaScript code. The web runs on JavaScript. It is the dominant programming language for writing browser applications, and thanks to the Node.js runtime, it is increasingly common to see it on the backend too. The quality of JavaScript code is crucial for security of web applications. This course, however, is not about general web application security. We will not address problems that can affect applications written in any programming language. In this course, we focus on security issues that are unique to JavaScript and are a result of its dynamic nature. I will teach you how to identify such vulnerabilities, how to fix them, and prevent those issues from creeping into your code. In this module, we will focus on the fundamental role that JavaScript plays in web application security. JavaScript can contain vulnerabilities, but in some cases it may even become an attack vector. There are two popular environments for running JavaScript code, and both of them have very different security properties. First, we will take a look at how browsers run JavaScript, and then we will see how Node.js is different. Then, we will look at language features that may lead to security vulnerabilities: dynamic typing, dynamic code execution, and prototypal inheritance. We will wrap this module up with an example of a simple coding mistake, literally just a missing character, that leads to a significant leak of sensitive data. Information security professionals are well known for specific jargon they use. We will not use it here, but it is important to understand some basic concepts of web security. Attacks against web applications are carried out by people. You may have an image of a person in a black hoodie typing at their keyboard in their basement, but the reality is much more nuanced. Attackers differ based on their capabilities and motivations. They can be teenagers wanting to impress their friends, fired employees seeking revenge, as well as criminals breaking into applications for money. Attacks would not be possible without vulnerabilities. Vulnerabilities are technical flaws in the system that allow people with malicious intent to break into our applications and systems. They can be simple bugs in the code, fundamental architecture flaws, or configuration mistakes. All of them can lead to data breaches. Those that usually hit the headlines are about leaking millions and millions of sensitive data records, such as credit card numbers. Data breaches can also involve abusing application functionality, for example, to order goods without paying, or getting a refund for goods that were never purchased in the first place. The most common web application architecture has three tiers: the browser, the server, and the database. JavaScript code can run both in the browser and user's device, such as a laptop or a smartphone, or on the server using Node.js. Vulnerabilities in server-side code may allow attackers to breach access to the application data store. Successful attack in a database may lead to a data breach that involves many users. The impact of a vulnerability in client-side code is typically limited to a single user. That sounds like good news. Unfortunately, bugs in JavaScript code running in a browser may allow attackers to impersonate the victim and to perform actions on their behalf. In this case, the vulnerable JavaScript code becomes an attack vector. JavaScript was created to add interactivity to HTML pages. Web browsers are the native environment to run JavaScript code. In fact, JavaScript is the dominant programming language in this space. When the user visits a web page, the browser downloads the HTML code of that page, as well as all the other assets needed to display this page. This includes CSS style sheets, images, and JavaScript code. Browsers allow users to visit multiple pages at the same time in tabs or separate browser windows. This means that at any given time, JavaScript code downloaded from several different sites is executed in the same browser. If one of those sites is infected or even owned by the attacker, aren't we at risk of malicious code stealing our data from legitimate sites? Luckily, browsers do not allow for this, and every website executes JavaScript code in its own sandbox within the browser. Code from one website cannot access data or functionality from another website. This is one of the most fundamental security properties of the web. Some browsers use very sophisticated sandboxing mechanisms, like running each tab in a separate operating system process. Downloading the code over the secure HTTPS protocol and using sub-resource integrity, or SRI for short, prevents attackers from injecting their own malicious code into benign sites. JavaScript code running in the browser is restricted in what it can do. It has no access to local resources on user's computer, and this applies to devices such as webcams or microphones, the file system, and the local network. The code can use those resources only using very limited browser APIs. This allows the browser to minimize the attack surface and ask the user for explicit consent for using those resources. Code originating from different sites cannot access each other's data and functionality. This allows for even stronger protection of data and code execution within the browser. Node.js is a runtime environment for JavaScript based on the V8 engine built for the Google Chrome browser. The unusual thing about it is that it allows JavaScript code to run outside of the browser. It has gained a lot of popularity and has proven to be a popular tool to build command line programs and web applications. It is quite different from the browser from a security perspective. Browsers download the code, and Node.js loads the code from local files, much like other popular programming languages. The permissions model is also different. Browsers treat the code as untrusted and restrict capabilities it has access to, and Node.js treats the code with full trust and grants access to all the privileges and the operating system user has access to, including devices, files, and the local network. Attack based on a security vulnerability in the browser may affect one victim at a time. Bugs in Node.js may allow for full server compromise, potentially leading to a serious data breach. JavaScript is a little bit unusual programming language. Its rapid development and massive popularity gave us several language features and coding patterns that may easily lead to exploitable security bugs. JavaScript variables can refer to objects of different types. In statically typed programming languages, variables can only store or reference values of a particular type. An integer can only store numbers, never strings or objects. In JavaScript, a variable can refer to a number, a string, or an object depending on the flow of control. When you look at the code, you do not always know the types of your variables. It may lead to unintentional information disclosure or other security bugs. JavaScript programs can invoke JavaScript engine at runtime. It sounds like a really powerful feature, and it is. It allows for easy processing of complex data formats, such as mathematical formulas, or implementing applications that users can extend with their own JavaScript code. Unfortunately, this is also what attackers dream about: the ability to inject their code into your application. JavaScript has a pretty unusual inheritance mechanism. Most mainstream programming languages use classes to express static hierarchical relationships between types of objects. In JavaScript, the same goal is achieved by building dynamic relationships between individual objects. Each object has a parent object, the prototype, it inherits properties from. If attackers can modify the objects forming the prototype chain, they may alter the behavior of your code in unforeseen ways. The dynamism of JavaScript is powerful and flexible. It facilitates rapid development and unlocks programmer productivity. If the same dynamism is abused by attackers, it can lead to security vulnerabilities. Now let's take a look at a sample application implemented in JavaScript. It is a part of an e-commerce system for specialty coffee lovers. In a true startup fashion, it was built fast, and truth be told, some things might be broken. The development team thinks there might be a few security issues here and there. The first area of concern is the login screen. It looks simple at a glance, but it has some smarts in how it tracks where the user was coming from before they logged in. We will take a closer look at that functionality. The second area that needs attention is user profile management. The implementation uses several programming idioms that depend heavily on the dynamic nature of JavaScript. We will inspect the code of both of those features throughout the course. We start on the home screen with the list of coffee beans sold by Wired Brain Coffee. The first functionality is the login screen. We type in the email, and we are in. Notice that now user's email is displayed in the top right corner and the logout button is visible. Now that we are logged in, we can also access the user profile management screen. It is quite simple and allows us to edit the shipping address. The email field is read-only. Let's log out, and let's go to the profile management screen again. It looks like we first need to log in before we can edit the profile. Notice that now we are taken back to the login screen that has the return URL stored in a JSON object in a query string. User session is implemented using a simple cookie that contains user email. We can easily display it using the browser development tools. Now, let's take a closer look at how this functionality is implemented. The Wirebrain Coffee e-commerce application consists of two components, server and client. The backend code is implemented in JavaScript using Node.js and the Express framework. The details of this framework are not relevant for this course, but it allows us to easily handle serving JavaScript code as well as CSS and HTML assets. It also allows us to dynamically generate and serve JSON documents. All those files are served by the server to the browser. Let's take a look at the server code. The app.js file configures the Express framework to serve static files, parse JSON documents, and handle HTML forms. The code in login.js handles the login form. It first reads email and password from the form and checks if they match the users in our database. This is a sample application, so storing user information in a flat JSON file is good enough. If the user credentials are verified, the code sends the cookie back to the browser and redirects the user to the return URL from the JSON object from the query string. If the credentials are not verified, the code returns HTTP 401 code. The code in logout.js is very simple. It removes the cookie and redirects the user back to the home page. Profile.js has two functions. One of them is responsible for reading profile information from the JSON file based on some search criteria. The criteria are sent in the field and value query string parameters. Then we filter the user database based on those criteria. The results are sent back to the browser in a JSON file. The function responsible for saving the profile information is a bit more complex. First, we find the user based on the email field. If the user has been found, we clone the field from the request using a JavaScript idiom that merges the request object with an empty object. Then we assign all the fields from this copy to the user object in our user database. Then we return the user profile in a JSON file. I'm sure you have noticed a few helper functions defined in utils.js. The filter function returns those elements of the items array where a given field matches the provided value. The getParams function retrieves an array of values from the query string object. The values are retrieved by names specified in the params array. The function also gracefully handles missing values, returning null, which is JavaScript value to denote missing data. The merge function performs a deep recursive merge of properties of the source object with the properties of the target object. Using such a function with an empty object as the target is a popular JavaScript idiom for performing deep copies of objects. JavaScript has a dynamic type system. It means that variables can reference values of different types throughout their lifetime. At one point, a variable may refer to a number, and it may refer to a string later on. The rules that describe how operations are applied to values of different types are quite complex and can lead to security issues. When JavaScript code attempts to perform an operation on two values of different types, it needs to convert them to a common type where that operation is well defined. For example, adding a number to a string will convert that number to a string, and the addition operation will become a concatenation of two strings. This may lead to unexpected code being called if types of variables are not properly tracked and controlled. JavaScript has two comparison operators: strict, also known as triple equals, and loose, known as double equals. The strict comparison operator compares both the value and the type, so a string can never be equal to a number. The loose comparison, when applied to parameters of different types, automatically converts the operands to a common type to make the comparison possible. When using this operator, a string can, in some cases, be equal to a number. Comparing values such as null and undefined is another corner case. Strict comparison will always treat those two values as different, but the loose comparison will treat them as equal. This may lead to security checks being bypassed if they use loose comparison and variable types are not enforced. Another aspect of JavaScript dynamism is that it used to be very forgiving of programming errors. Over time, it became clear that certain language features, like giving any function an ability to define a global variable, are dangerous for security and the correctness of the code. Newer versions of JavaScript allow the code to run in so-called strict mode that prohibits some of the problematic behaviors. Strict mode is enabled by putting the useStrict string literal at the beginning of a script or function, and it should always be used when writing JavaScript code. Let's get back to the code of the Wired Brain Coffee application. Let's quickly review all the code files for use of loose comparison operator. If we find it is used in a security check that operates on untrusted input data, it might be a security vulnerability. Looks like the double equals operator is used in the filter utility function and is called from the read profile function. Now let's take a quick look at how to exploit this bug. We identified a potential vulnerability. Now we need a way to make use of this bug to either steal sensitive data or abuse functionality of our sample application. There are a few ways to make use of automatic conversions and loose comparison to invoke an unwanted or unexpected behavior. We can try to use numbers instead of strings. We can use arrays where objects are expected. We can also remove properties that get the JavaScript value undefined. When we have identified input that may potentially lead to an attack, we should work backwards from the vulnerable code to the input data to try to find a way to deliver it to the vulnerable piece of code. When we have that, we can inspect the HTTP requests and responses using browser developer tools or proxies such as Fiddler. The next step is to modify legitimate requests to include malicious data. Finally, we send such modified requests to the application. Let's see how we may do this for the loose comparison we found in the filter function. The loose comparison tries to compare a field of an object, provided as an input parameter, to a specific value, also provided as an input parameter. Both the field and the value are taken from request parameters in the read profile function. If we could trick the filter condition to always be true, we would be able to retrieve information about all the users in the database. If the field did not exist, the property retrieval, the bracket notation, would return undefined. If the value was null, the loose comparison would always be true. Luckily for the attacker, it will be null if it is missing from the query string, thanks to the getParams function. Let's see how we could do that. The first step is to capture the legitimate request. Let's open the browser developer tools and let's inspect the network traffic. The request has a field name and value in the query string. The response contains an array with a single user object matching the provided email value. Now, let's modify the request. Let's remove the value from the query string and let's change the field name to an invalid value. It's time to send such a modified request to the application. The response now contains information about all the users. Our attack has been successful. Now, let's see how to fix it. There are several ways to fix security vulnerabilities coming from JavaScript dynamic type system. Using strict mode is a no-brainer, except for cases where backwards compatibility is a concern. All code should run in strict mode. Using loose comparison can lead to strange bugs, and when used in security checks, it can lead to their bypass. The strict comparison operator, or triple equals, should be used instead. Object equality can also be checked using the object.is method, which works almost like triple equals, except for a few corner cases related to numbers. Untrusted input should always be subject to data type verification. All data coming from outside of the application might have potentially been tampered with by the attacker and may cause unexpected type conversions and unwanted behavior. Now, let's fix our vulnerability. The simplest way to fix the loose comparison vulnerability is to replace it with the triple equals operator. Now, let's see if this stopped the attack. Let's send a malicious request again. We need to remove the value parameter and change the field parameter to an invalid value. Now we get the expected result, an empty array. The array is empty because the comparison operator correctly distinguished between null and undefined. If this behavior still seems a little off to you, you are right. We are still relying on arcane rules of comparison of null and undefined values. The input data validation should be a lot stricter and reject incorrectly formed requests. Let's add validation for the field and value parameters and return an HTTP 400 code to inform the caller that the request was malformed. We need to check if the type of both field and value variables is a string. If it is not, we have to return the error code and skip the rest of the read profile function. Let's send the malicious request again. Now the server properly responds to a malicious attack. We tightened our defenses by verifying that all required parameters are indeed present and that the types are what we expect. In this module, we covered which JavaScript features may lead to security bugs. We have seen how the dynamic type system may lead to disclosure of sensitive information. In the next two modules, we will dive deep into dynamic code execution and prototypal inheritance, and we will see how these features might be exploited. We have also taken a look at two most popular environments for running JavaScript code, and we have seen how different they are from a security perspective. Browsers run JavaScript in a secure sandbox, but bugs may be used as an attack vector. JavaScript code running on Node.js has all the privileges of the operating system account it runs under, and the bugs may lead to a full server compromise. You will see one such vulnerability in the next module.